So since this is a symmetric problem, we can double up the energy of cables 2, and then we could double up the energy of cables 3, and we're left with an expression, the integral of F1 d delta 1, 2 times the integrals of F2, 2 times the integrals of F3. Now I'm going to flip this into an expression for delta using the stiffness term, AE over L. And pretty straightforward here, I think. And we integrate, and we have U. So now something kind of fun happens here. In this problem, we notice that it just so happens that the cable 1 is perfectly aligned with P. Okay? So that's super convenient, because what can we pull out? We can pull out the force of cable 1 if we differentiate it with respect to the deformation of cable 1. So let's take a look at that. So what I'm doing is I'm going to differentiate this previous expression U with respect to delta 1. And the only thing that stays alive is the first term in here. In this first term in here, there is no chain rule, because we have the 2 over the 2 plus partial delta 1, which is 1. In the next one, we do have to chain rule it in here. So we have 2 delta 2 times partial delta 2 partial delta 1. So that's exactly what's happening here. 2 delta 2 times partial delta 2 delta 1. And the third one, chain rule in here, we have the 2 delta 3 and then partial delta 3 delta 1. Now these are kind of funky. Partial delta 2 partial delta 1. And your author has tremendously helpful images here, so that's why I think it's worth exploring this example in some detail, and we're going to, of course, do this for homework. So what's going on here? Take a look at page 421, and let's zoom in on 2 cables. So I made the vertical cable a red cable, and I made cable 2 a blue cable here. So what's happening is that we stretch this point down. We know it's not moving left and right because of symmetry. Well, how much does delta 2 stretch given a delta 1 stretch? And I hope that you've seen something like that at some point in your careers before. We replace arc lengths with straight lines. That's a right angle in here. It's an approximation, but these are super small, so it seems to work pretty good. So delta 2 is, of course, delta 1 times cosine alpha 2. So delta 2 over delta 1 is cosine alpha 2. But that's not quite exactly what we need. We need partial delta 2, partial delta 1. And I think the best way to think about this is that this is a rate of change, okay? So as delta 1 grows, so does delta 2 grow through this ratio cosine alpha 2. So cosine alpha 2 is partial delta 2 delta 1. And then similarly for cables 1 and 3, the cable 1 being the red cable, cable 3 being the blue cable here, the rate of change is going through partial, is cosine alpha 3. So that previous expression that we had, now these just become cosine alpha 2 and this becomes cosine alpha 3. Okay? And then there's one more little simplification here. There was a delta 2 previously in here, and I just popped in delta 2 is del 1 cosine, and then there was a delta 3 in here, and I popped in del 1 cosine alpha 3. So we pull out some stiffnesses, and we have cosine squared terms in here. So it's really sweet.